We're going to look at the third part of similar shapes now. So this time we're going to be talking about the volume of similar shapes. So very similar to my last video where we were looking at the areas, I've actually got the same rectangle here so that you can compare the two and see the similarities, if you pardon the pun. But what I've got here is I've actually now turned them into cuboids instead of just simply having the rectangle, so they're now three-dimensional shapes. So here I'm telling you that these two cuboids are similar, and you would have to be told they're mathematically similar, just like the area ones and just like length ones, where you're looking at just the lengths on shapes as well. You either need to be told that they're mathematically similar, or you need to be able to work out that they're mathematically similar. So I'm telling you these are mathematically similar. And just to recap again, that means that all corresponding angles are the same, and all the lengths are in the same ratio. So if we know the lengths are in the same ratio, on this particular example here, we could be asked to find this length of y. So you need to find the common ratio between the corresponding sides. So it should be quite straightforward for you to see that if we compare the 5 with the 15 and the 4 with the 12, we have that same scale factor that we had in the area video of 3. But just to clear that up, let's just check this. So our length scale factor, I'm going to just abbreviate that there. The length scale factor, again, you do the biggest one divided by the smallest one to keep it nice and simple. So if we use the 15 and the 5, 15 divided by 5 is 3. Equally, we could have used the 4 and the 12. So if I just put that there in brackets, we would have also got 3. They have to be the same, otherwise they're not mathematically similar. So with that in mind, we know that's the case. What we can therefore do is we can actually find out what y is, and y will therefore just be equal to the corresponding side on this shape, which is 8. We're going from small to big. Small to big means that we multiply because we want it to get bigger. So we're going to do 8 times by 3. If it was a length on the smallest shape that was missing, we would divide. We would do whatever the length was here divided by 3. You can see 15 divided by 3 gives you 5, 12 divided by 3 gives you 4, and so on. So 8 times 3 in this particular instance is 24 centimetres. So we know that y is 24 centimetres. Now, if we therefore then look at the volumes of the shape, and again I have picked something nice and simple so we can focus on the similarity rather than finding the volume of a complicated shape. So with a cuboid, it's just length times width times height. So here the volume of this one would just be 4 times 5 times by 8. Okay, and the volume of that shape is actually 160 cubic centimetres. Same principle here. So the volume of this shape would be, I'll try and keep them all in the same order. So here the 12 times by the 15 multiplied by y, which we now know to be 24. I don't expect you to do that in your head unless you're really good at multiplication. It is 4320 cubic centimetres. Okay, so those are your two volumes. Now again, it's probably a little bit more difficult to spot the pattern this time than when we had the area one, just because the numbers are so big. But get your calculator out and have a little look. So what we find this time, if we take the volume of the bigger shape and divide it by the volume of the smaller shape, we actually get a really interesting result. So this we're going to call out volume scale factor. So we take the bigger one, which is 4320, divide it by the smaller one, which is 160. And if you do that, you actually find you get the number 27. You might think, well, that doesn't seem that remarkable, but actually 27 is really important, because remember our length scale factor was 3. And what's the link between 3 and 27? Well, actually 27 is 3 cubed, and that is no coincidence. Again, very similar to with the area question. Don't forget, each one of these numbers here has been multiplied by 3 over there. So we've still got 4 times 5 times 8, but we've times by 3 times as well, which is 3 cubed. So that 27 is actually just 3 cubed. And much like we had with the area question, it will hopefully be no surprise to you that we can use this rule. If the length scale factor is k, then the volume scale factor is k cubed. And that is a really, really important result. So now we can put that together with our area result, and we now know that if we have a length scale factor of k, the area scale factor is k squared, and the volume scale factor is k cubed. And that then means we can answer now any question with 3D shapes in it, whether it be to do with lengths, with areas, or with volumes, and you just need to know which one it is that you're comparing. So let's look at this question, because it's slightly different in the way it's set up to the area one that I did with you before. So in this case, again, I'll fill in the gaps for you. You would be told that these are mathematically similar, and in this case we're given, for the smaller shape, we're given the radius and the volume, and for the bigger shape we're given the volume and we're asked to find the missing radius. So we're told they're mathematically similar, and that is the key. And to begin any of these questions, the first thing you must do is to find the scale factor, whether it be the length one, the area one, or the volume one. So in this case, the only thing we've got for both is the volume. So we're going to find the volume scale factor. Now, just like with all the other questions, do the bigger one divided by the smaller one because the maths is easier. So we're going to do 500 divided by 4. And 500 divided by 4 is actually 125. So that is the volume scale factor. Now then what you've got to work out is, well, what scale factor do you need? And in this case we've been asked to find the radius, and the radius is a length. So we need to know the length scale factor. So bearing in mind this relationship here, we know that that is the length scale factor cubed. So if that's the cube of the length scale factor, how do I get back to it? Well, I just cube root. So the length scale factor is the cube root of 125. Now if it's on a non-calculated paper, it will be one that you should recognise, and I would make sure that you know most of your cube numbers up to about 12. The cube root of 125 is 5. So that makes it all of a sudden a lot easier. Okay, it might seem quite complex, but if you think about it, 5 times 5 is 25, 25 times 5 is 125. Okay, and now we have our length scale factor. We just need to decide, well, are we going to multiply or are we going to divide? In this case, we've got the smaller length, we want the bigger length, so we are going to multiply. Okay, small to big, we multiply. So x, our missing length, is just equal to the length on the smaller shape, which is 2, multiplied by our length scale factor, which is 5. I think we can all do 2 times 5 is 10, and don't forget your units, and it's a length, so it's 10 metres. Okay, it's very important that you get your units correct as well. So just to recap, always find your scale factor, whichever one it is, then convert that to the scale factor you need for the question, decide whether you're going to multiply or divide, do your calculation, and there you have your answer.